ahead and start recording then, since I think the doorbell has stopped ringing. I think that means we're all here. So happy Thursday. Happy Garbage Day to those of you celebrating from the greater metro area here in the corridor. We have homework 4 due on Monday. Yeah. So how's that going, folks? Does anyone want to talk to me about that or ask questions? Go for it.
So, I within cluster centered something, and the mean of all of them is now 0.
Yes. That's as it should be. If you cluster mean center a variable, the mean should be 0 to several decimal places.
All right. Never mind. I'm going to stop talking to the audience then.
I did not mean to cut you off prematurely.
No.
But that's where I thought the question was going, is did I do something wrong?
No. Yeah.
You did not.
All right. I don't know if we reviewed that, so.
There was a series of questions in that vein in homework 2, maybe? I know I asked for means and standard deviations of various variables to make that point, so, yes. Any other questions or things folks want to talk about? If you're saying to yourself, God, it feels like I'm spending all of my time just getting my data set up, yes, that is correct. In the real world, that is how it works. I will spend 80% of my time just getting the data set built, everything coded, everything checked, everything merged back together. You cannot underestimate the amount of time that takes.
It's just like a R question.
Okay.
Or maybe whatever software package we use.
Okay.
But like, as we recode variables within, like, from our data set, so making like 1s, 0s, 2s, 1s, etc. After we do that, is there ever a way to save like the new data set that we've recoded like to an Excel file?
Yeah, I'm sure that there is. Yeah, there's an export command is what I would look at. I don't know what it is for R off the top of my head. It's literally proc export in SAS.
R is just like download .csv or whatever.
Write CSV.
Write CSV, yeah, that sounds right. Is there a dot in between?
Yes.
Write .csv.
Write.csv, the name of the file, the path, and the name of the new file.
That is
CSV.
wonderful
Yes.
and handy.
Yes, yeah,
Thank you.
yes, thank you, Charlotte, a dot in between there. Just pro tip though, when you're recoding variables, do not recode them into the same variable, make a new column. Because if you screw up, you can't get it back. If you're writing over the same column, then that's bad. Plus then it gets confusing if you have the original documentation for what that column meant and it no longer matches the values that are in it. Future you will be confused and unhappy with current you. So make future you happy by making a new column and adding somewhere what it means. Another thing to think about is leaving yourself a trail of breadcrumbs in your code when you're doing all these transformations, not just what you're doing, but why. Like, why did you change the 2s to 0s? You know, like future you will appreciate that reminder when you're looking back at this. So, all right, well, I'm not a lot of questions then thus far. Comment, you can also use the package APA tables, or APA tables, I'm guessing, and function apa.core.table to spit out a correlation table to Word that's already formatted. What a wonderful thing. Great. Yes, and if you don't have that, I was going to point out a resource in Excel that I like to use whenever I'm doing a quick table out of output. We open up something here under data. There's something called text to columns where you can paste in output and it will figure out what the column should look like and turn it into column output. So that option I use when I'm formatting like M+ output, or sometimes R, or anything that's ugly and not like built into a table. But if you can get a function to do it already with less copying and pasting, that's much, much better.
So what was that?
It's under data, it's text to columns is the function. In R?
Yeah.
It is lowercase APA, capital T, and then ables. It looks like APA tables. And there's a function inside it that is all lowercase apa.core.table. 1R on the core. All right, So then, let me know if you need help with homework. If you have questions about what to do, has to be 3/4 complete for me to take it as a draft, but it doesn't have to be perfect. So don't let perfect be the enemy of good. Good enough. In other words, do as I say, not as I do. All right. How about a little review time? Would that be good? Jumping into things? I feel like I could just like use a minute to just remember what the hell we're talking about. So,
Yes, I have a quick question now.
yeah.
Lisa, we know that when we have random slopes, we can use that random slope variance to build some confidence intervals
Yes.
to try to see what's the effect size of that predictor across groups, right?
Yes. I think of it as a way to convey the relative size of the variance in units that should be more understandable than a variance. Yes.
Yes, because maybe the slope is positive, but for some groups can be even negative sometimes.
Yes.
Now, my question is, when we have these generalized multi-level models, and we know that variance will change when we add new predictors to that model. So, in this case, that confidence interval is specifically tied to the version of the model we have.
Yes.
Because if we change something, the variance can change, so that confidence interval can be.
It will widen. Yes.
Okay.
Yes. Yeah, so the question was, if you're going to compute a random slope confidence interval to describe the expected variation of the slopes across clusters, you should be clear what model that came from, because it
Okay.
would be a different number from any other model based on what has been added to explain variance at what level.
Great. Even if that's a random slope, because it is a variance component at the end, right?
It will increase. If you explain residual variance, everything else goes up.
Okay, great.
Okay, so generalized, let's start it there. What's that word mean?
Logistic?
Logistic?
Logistic regression?
Logistic regression is a generalized model. That's one case, yes?
Okay.
Okay.
Not normal data.
Not normal, yeah. That's the way I talk about it. A generalized model is a way to predict an outcome whose residuals are not normally distributed. So the residuals is what we make assumptions about, but the shorthand for that is not normal outcomes. That's the ized part. So general means normal outcomes, ized means not normal. And what makes a generalized model different? Like, what do we have to do to it to predict a binary outcome, for example? More work. Yes, that is correct.
Your
Transform the data with a link function.
Not the data, though. Close.
The means.
The means.
unbinding it.
Yes, and I'll take gestures.
Well-
This is my usual gesture for that, for whatever
So
reason.
unbinding to bind it within the 0, 1 framework,
Yes. So here's an example of a link function, for instance. I like this picture that I stole from your textbook. So for instance, the logit is a link function. It is the log of the odds of the probability of a 1. Commit that to memory. You will need it in your life. Just learn that. Seriously, because logits show up everywhere. Like if you take SEM next semester and we have binary outcomes that we're going to fit a measurement model to, guess what? It's factor analysis on logits. It's all the same thing. So if we have a logit link, it takes the conditional mean to be predicted, which in this case is the probability of a 1, and it stretches it out onto a metric that is truly continuous and unbounded. That way we can have a linear slope keep going forever and ever as usual, but what it's predicting is a logit. Then when we back translate that logit into the corresponding probability, back translate is called what more formally? Inverse link, yep. Yeah, because I'm giving you the Lisa version and then the how to write it in a paper and not sound, crazy version, right? You can't say unlogit in a paper or back translate, but you can say inverse link. So we go from logits back to the conditional probability. That's an inverse link. And what it is in this case is e to the logit over 1 plus e to the logit. Another formula that would be helpful to just put in the top of your head. So there's 3 different scales then that are involved in terms of predicting an outcome. We have probability, which 50-50, 0.5 is the neutral point on that scale. If we take probability of a 1 and divide it by the probability of a 0, That gets us to odds. And neutral point in odds is what? And feel free to read from the screen.
1.
Yeah, 1. So probability of 0.5 converts to an odds of 1, and then if we take the natural log of that, it's 0. So logit of 0, odds of 1, probability of 0.5 is the neutral point on each of these scales. Not yet. Odds is just odds. Odds is the probability of a 1 divided by the probability of a 0. If you do that and like stack it on top of another one, and you talk about how it changes, that's odds ratio. Yes, this screwed me up for a very long time because odds is a ratio, but it's not an odds ratio. Of course not, right? That would be too easy to just name it like what it is. So we need link functions whenever we have what kind of outcome? Bounded, yes, that's the problem that link functions are solving. They are trying to make sure your predictions stay within the limits of what the outcome could possibly be. So we predict a probability that is bounded by 0 and 1, for instance, or a proportion that's bounded between 0 and 1. So that's one new thing, is a link function, to make sure that our predicted outcomes stay into the range they're supposed to be. What else makes generalized models different? Distribution. Tell me about that. Different distribution for what's left over at level 1, which I usually talk about as residuals, but I don't think that's technically right anymore. But you can keep the idea in your head. Yes, so level 1 is what changes. Does level 2 change in these models? It does not. Level 2 stays multivariate normal. The U's are always multivariate normal. It's the level 1 conditional distribution that might need to be something else. The only one I think we've talked about thus far is Bernoulli, which is for a binary outcome. Looks like that. So Bernoulli gives you the probability of a 1 if that's what you got, or the probability of a 0 if that's what you got, as opposed to normal, which is this scary thing right here. And there are multiple different kinds of distributions that go with different kinds of generalized models. And then, so we have a link function, we have a different kind of distribution. What's the third piece?
Our linear model?
Yeah, the regular old linear model, which is called the linear predictor. And it includes both fixed effects and random effects when you're doing the multi-level model version. All right. Okay, do you want to go over this? Review this? How to go back and forth across things, and we'll get some examples of this as well. This is slide 18. So if I have my linear model here predicting the logit, so the probability of a 1 divided by 1 minus that, which is the same as saying the probability of a 0, take the natural log, that thing is logit. So the predicted outcome by the model, I've put a y hat here on it, this is a single level example, is given by this thing. So as long as you say in logit y, you can interpret all of these beta coefficients the same way as usual. So beta 0 is the predicted logit y when your predictors are 0. Beta 1 is a change in logit y for a 1-unit change in x1, and so forth. So as long as you say in logit y, you can talk about this the same way as usual. If you want to provide effect sizes for your slopes, that's where we get into odds ratios, which is e to the slope. And that puts it into a metric where, what's neutral again in odds?
1.
1. An odds ratio for a positive slope goes from 1 to positive infinity. An odds ratio for a negative slope goes from 0 to 1. We can't then convert the slope into probability. It doesn't work. What we can do is go through this column instead. So the order of operations is use your logit coefficients to create a predicted outcome in logits. Then translate that predicted outcome either into odds or probabilities as you see fit. Usually it's probabilities is what people would do. All right, what else did we talk about last time that makes these models different than the standard multi-level models? What's a consequence of the fact that we don't have a separate residual variance at level 1? So for instance, there's no e here in this equation. Where'd it go? What do you think? Either. So E is not here at the end of this equation, not because we're assuming it's perfect, but because E does not have an estimated variance. It's not a parameter anymore. E is dictated, like if you know your predicted probability, you can only be off by this much or that much to get up to 0, down to 0, or up to 1. And so residual variance is not constant. It depends on the mean. What is it if I have a logit model? What magic number do we throw in there instead? 3.29, or pi squared over 3, which is the variance of the logistic distribution. For binary data, the scale factor is 1, so it's just this part. So it sounds like it's just made up nonsense, but there is a reason. So this is 3.29. What if I add a super, super, super great set of level 1 predictors? Then what is it? 3.29, and that is the problem. So in standard logistic regression for single level models, there is not such a thing as a uniquely defined R-square. There's like 14 of them that people have made up, and I'm not exaggerating. You can ask for extended fit statistics from R or from Stata, and they will list all kinds of R-squares. And they can range quite widely in terms of what they report. So there's different ways of trying to approximate an R-square, but because we don't have an estimated variance at level 1, it can't come down. We can't use it for that purpose. So what people do instead is odds ratios. What about level 2? Can we estimate a random intercept variance?
Yes.
To describe the amount of dependency? Yeah. Can it be whatever number at once, or is it tied to something?
It's a logit scale, but can be where.
It can be whatever at once. It's in logits, whatever that means, but it can be whatever at once. So if I add a super, super great set of level 2 predictors, can my random intercept variance go down? Yes, it can. So at level 2, things work as normal, pun intended. See? Wait for it. You hit it. Yeah, okay. Ba-doom. So level 2 is not the problem. It's level 1. Do you remember the difference in terms of how we talk about the fixed effects? We started talking about that a little bit last time. Let me get to something about that. Is that one? So like this fixed intercept here. Normally, how would we describe that? The mean of the cluster means. Can I say that anymore? I cannot. I have to add something to it. This is the expected cluster mean specifically for a cluster with a random intercept of 0. It's a unit-specific interpretation is what it's called. We have to talk about it that way. It's not actually the mean anymore. It's closer to what the median would be. Yeah, I think those are the high points of what we talked about. That sound familiar? A bit? Okay. Now, I hate to do this to you, but I got to talk a little bit about estimation. Just like this much. I know. It's because I know this much. And so that's all I can do is give you this much. And then we're done. Then I'm out. But what I want to do is give you some vocabulary words to look for in your software packages so that if you see these words, you know what it's doing. Because in these models, you can get very different results based on what type of estimation approach that you use. So I just want you to be aware of some of the choices and what you can and can't do as a function of those choices. So I'm starting on slide 36 for right now here. So we still have the same end goal. We're trying to find the model parameters that make our data the tallest, and that's the maximum likelihood solution. So when we're in normal land, where we've been up to this point in the semester, we have level 1 residuals that are supposed to be multivariate normal. Usually we don't put any correlation in there, but multivariate still because it's multiple people per cluster. And at level 2, those are supposed to be multivariate normal. So you can put those two things together, and it forms a nice, easy distribution that you can, the term for it, I believe, is closed form. Like, people can figure it out without having to do extra work. In our new generalized world, level 1 isn't normal anymore. level 1 is Bernoulli or multinomial or Poisson or some other kind of distribution. But level 2 is normal. And so you can't put them back together into one thing anymore. I once had students try to name what that would be. If I have a Bernoulli level 1 and a normal level 2, they wanted to call that Bernormal or Normuli. I like Bernormal myself. I like that one, but Normuli also works. But be that as it may, you cannot figure out what the probability is of the Normuli distribution because it is not a thing. So what has to happen then is we have to figure out a way to remove the u's from the equations in order to figure out what fixed effects are going to make the data the tallest. In multivariate normal land, we didn't actually need to know what the u's were, because if everything is normal, then the mean, variance, and covariance are sufficient statistics to describe them. But that's not the case anymore. So we have to figure out what to do with the u's. And it's going to involve a process of trying on multiple potential u values and then figuring out what the likelihood would be in each case. That's what's going to happen.
So, what you just said, did you just say, basically, with the first option, you can kind of calculate it, and standardize in some sort of way, and the second option, not so true?
Yes, I would say that's a good synopsis. In the first case here, if you're willing to assume that your residuals have a multivariate normal distribution, and that's true at level 1 and level 2, which means you can put them together into something called a V matrix, then you don't need to know what the actual u's are. All you need to know is their mean, variance, and covariance. And those are model parameters, essentially. Means are 0 because those are over in the fixed effects. Then we figure out what the random effect variances and covariances are, what the residual variance is, and we put that all together. But if the u's, if the level 1 distribution is not normal, then the u's are we have to know what the u's are, basically. Like there's no shortcut to it. So there's 3 different families of approaches: quasi-likelihood, numeric integration, and Bayesian land. So pseudo-likelihood or quasi-likelihood. This is an older set of methods. It's what people did before they could do other things. They don't work as well. So as far as I know, the last I checked, this was the only option available, for instance, in SPSS in their generalized linear mixed models package. So that's a good example of why we don't teach in SPSS, because the ceiling is lower relative to what it has in it. It's the default in a number of packages, including some of the stuff I found in R. So this tends to underestimate variance components, and it also is not a true likelihood. It's an approximation. It's missing the normalizing constant that would make the entire area under the distribution sum to 1. So what that means in practice is that you cannot do -2 log likelihood differences when you're in this estimator. They're just, the likelihoods aren't on different scales. So then you're like, well, how do I test random effects? Well, I don't know. I guess you just look at it and say, that looks big to me. I don't know how you would do it. Yeah, because the Wald tests aren't supposed to be good for that either. So watch out for this. In R, I tried to use something that was trying to do this, and I used ANOVA, and it warned me that likelihoods were not comparable under these methods. And I'm like, oh, that's what it's doing. Good to know. So we're staying away from those for the most part. What is considered the gold standard of estimation, if you're not in Bayesian land, is something called numeric or numerical integration. I've seen it written both ways. This is otherwise known as marginal maximum likelihood. If you learned about it in the IRT class, yes, this is the same thing. Synonyms for this is Gaussian quadrature. Gaussian means normal. So it means we're going to take the normal distribution and sort of carve it up into rectangles to try to figure out the area under the curve that way. This can take forever to estimate, particularly as you increase the number of random effects. There is a simpler version of it called Laplace estimation that you will see being used in R. It's the only option once you add random slopes in Glimmer, I learned. This can be sped up by start values, so you can get start values from less good methods and feed them into this to make things go faster. It still relies on the same assumptions of local independence, that the level 1 residuals are independent after we control for all the fixed and random effects. And for those of you who are familiar with the longitudinal options in terms of R correlation patterns among the residuals, those aren't a thing anymore. The only way that you can introduce dependency is through random effects in these models. It's just not possible otherwise. So the way it works, step one, figure out some starting values for your fixed effects. So programs have various ways of doing that. We compute the likelihood of each observation given the current versions of the parameters using the chosen distribution of residuals, so Bernoulli, Poisson, etc. So the model is going to create a predicted outcome, but the U's are not parameters. All we need to know are their variances and covariances. So we proceed by assuming that the U's are multivariate normal, and we compute a likelihood for each set of parameters by removing the contribution of the U, and I've got an example of this on the next slide. That's what's known as integrating it out. It's accomplished by Gaussian quadrature, which is dividing up the distribution into rectangles and summing over them. Decide if the answers are good enough, which happens when the total height doesn't change very much across different versions of trying new parameters, and try new ones until you get to that point. And there's various ways of trying to figure out what you should try next. Most of them rely on some form of calculus to do this, and this is where I do not have any more information than this to tell you. Calculus, it's magic. The slope, it figures out where the slope is, because if it's, actually I do have this much more information. If it's heading up, then the slope is positive, and if it's at the top, it's 0, and if it's heading them the wrong way, then it's negative. Well, it's moving the wrong way. Yeah, it's negative, see? And then the second derivative tells you like how much you need to like make it go up faster. There, see, a little bit of calculus. But that's the end of the story. So this is what it looks like. So if I have a distribution of U's here, let's say that it's a normal distribution for the sake of the axis. Quadrature is the idea of dividing it up into little rectangles. And it's a way to figure out to approximate basically the whole area under here with different rectangles. So the number of rectangles is known as the number of quadrature points. This is something you will see in your software options. The default varies by software. Stata defaults to 7, M+ defaults to 15, Proc NLMX I think defaults to 30. You have to read your documentation to figure out what it's doing. But the more there are, the better it works, but the longer it takes. So there's a trade-off. So this is what it looks like. I'll put some numbers in here to try and make it a little bit more understandable. So let's say that our current values for a very simple model, I have a fixed intercept, I have a fixed slope of a level 1 predictor, and I have a random intercept. So just for the sake of demonstration, I made this a binary variable, but pretend it's not smushed, okay? But I don't have any room on the slide to add more stuff. It's already full. So here's my little model. So in order to figure out what the predicted probability of a 1 is, I have to know U, but U isn't a parameter. So what this is going to do is try on a bunch of possible values for what U could be. So let's say that if I have a normally distributed U, one choice might be -2. So if somebody has a predictor of x that's 0, then their predicted logit would be the fixed intercept of 0.5 plus 0, because x is 0, so that part drops out. And if I'm trying on a value of U of -2, I'll throw that in here. That gives me a predicted logit of -1.5. For somebody who has x of 1 instead, the predicted logit would be 0. Well, I don't know what their true logit is, but I do know what y is, because I have that in the data. I know for real if their y was 1 or their y was 0. So I can compute the predicted probability of each given the predicted logit. So logit of -1.5 is less than, it's a negative number, which means it's less than 0.5. That corresponds to a probability of 0.18. E to the logit over 1 plus e to the logit is how I got there. Here's the opposite of that, if the y is 0 instead. Same thing for x is 1. So if this is a person from the same cluster who got a 0, and this is a different person who got a 1, let's say that then I can multiply those together if they both got y's of 1s. And that's the result of multiplying these two numbers. So now we have to think about our choice of trying on a U of -2. If this is a normal distribution, how likely is it that someone has a U of -2? Like, where would -2 be in a normal distribution?
2 standard deviations below.
Yeah, 2 standard deviations below the mean, which is like not very likely. So we are going to downweight that guess with the probability of 0.5, and that u takes up, it's like a width of 2. So then that whole thing multiplied together is here. Now if we try on a different u, let's try on a u of 0. Okay, I'm going to plug u of 0 in here, figure out the predicted logit, figure out what the logit predicts the probability of each to do, multiply it. Now a u of 0 is smack in the middle, right? That's the mean. So that's pretty likely, so we're going to upweight that in terms of the probability with the 2 and do the multiplication. So this is what it would look like for 3 quadrature points. Each time it's like, what would the predicted probability if you were this, if you were this, if you were this? And then we add all that together, and that's the height for that observation.
Could you repeat, please, how those U0 block, the weights are defined?
This has to do with where, basically the amount of area that that rectangle is taking up. So the way this is divided up, it's like I've got 80% is like the middle U that's a 0, and then 10% on either side. So this is like dividing it into 3 chunks.
Great. Thank you.
Yes. So the number of quadrature points is the number of U's that you try. And this is a random intercept model, which means that I only have one dimension of integrating over. What do you think would happen if I had a random slope? How many U's would I have to try on then? Well, if I have 3 for one dimension and 3 for another, that's 9. Now what if I do the default of 15 like M plus does?
15,
15 by 15, 225. What if I add a second random slope? 15 by 15 by 15? I can't do that math. It's a lot though.
No.
It's a lot. So M plus and other packages will warn you, like, you just asked for an analysis with 5 million quadrature points. Are you sure you meant to do that? And sometimes it will just say, no, just no, I'm not going to do it for you. So this is one thing that can cause differences across packages in terms of the answers that you get, is how many quadrature points that it's doing and whether it's adaptive. Adaptive quadrature, by the way, first passes through the whole distribution, and then it does a second pass, like re-rectangling the spot that seems to be most likely to get it more precise. So most of these, if they're doing quadrature, do the adaptive version, but that's yet another option. So in the code for this example, you will see something related to int points, or nint, I think it is in R, for the number of rectangles being requested. That's what that means. There is, for certain complex models, it switches down to 1 quadrature point, which is something called the Laplace method, and I do not understand how it works. I've tried, and I'm just not going to. I've just accepted it. Because I don't understand how you can try on 1 U and have that be a thing, but somehow it works. So you will see the word Laplace attached to that, and that is a full likelihood. So if you're going through all of this, then at the end of what the result, you have a log likelihood value for your model that works the same as usual. We can do likelihood ratio tests and all that stuff. I would just try to make sure that if you're comparing models, that you keep this part consistent to make sure that everything is on the same scale in terms of the number of points and whatnot. All right, so there. Summary, what we talked about thus far. So generalized models used for outcomes that have boundaries. Linear predictor works the same as usual, but it's predicting a link function. And the linked outcome you can back translate into the data scale. Level 1 residual does not have variance anymore. That means that the model changes scale every time that you add a level 1 predictor. And estimation is trickier, takes longer, and does not come in Remmel flavor for true maximum likelihood. So this is the point where people would turn to Bayesian estimation, even if, like, philosophically they're not interested in a Bayesian analysis, just to make it work. Bayes can find results when ML cannot, when integration becomes too much. So that is more likely to happen anytime you're combining link functions and latent variables in some kind of an analysis. Random effects are latent variables. They're the same thing. All right. So that was a quick tour of estimation. Point of the story, quadrature, integration points, number of views, try it on at each step. Questions or comments? Okay, can we go back to the example? Everybody likes numbers better than that. Okay. So this is my admittedly silly example. We're predicting free and reduced lunch from math because I knew how to do that in the data set that I had. And as many of you can now understand, already having a data set that you're familiar with all the variables you need, all nicely organized, is a lot easier to work with than finding yet a new data set from scratch and having to go through all of that process. So please forgive me for taking the lazy way out. Example 6b is a brand new data set, by the way. And it has an interesting story to go with that as well. But we're not going to get there today. Okay, re-go over or review?
Review.
Review? Okay, because I think we've done this a couple times. So to start with, I'm predicting a binary version of this lunch variable where I collapsed the two reduced and free categories. I have an ordinal version towards the end of this handout. So first model that I did has no random intercept to it. So I'm calling this a single level model. This is a logistic regression. It's empty because there's no predictors. The purpose of this is to make sure I know what my software is doing. So if this analysis is going to be predicting the probability of a 0, the intercept I get back when I convert it to probability should match this percentage. And if the model is predicting a 1 instead, it should match the other percentage. So that's why I'm doing this, is to figure out which one it matches and therefore which way is up in terms of this analysis. So the fixed intercept I get back is in logits. E to the logit over 1 plus e to the logit gives me a predicted probability of 0.3, which is right here. So now I know it's predicting a 1. Huzzah. Once I add a random intercept, though, which I did in model 2, the fixed intercept changes, and the predicted probability that goes with it no longer matches the data. It's unit specific. So now, in a school with a random intercept of 0, the probability of any one student getting free or reduced lunch is 0.24, not 0.3. In terms of code, stata, int 0.7, that's me making explicit what the default is in terms of the number of integration points. Certain models default to other estimators, and so if you want to make sure that you know what it's doing, you can write it in the code. In R, I have lowercase n AGQ. Now you know what AGQ stands for. You're like, we do? Yeah, adaptive Gaussian quadrature, that's what that stands for. Number of rectangles. And I picked 7 because that's what stata defaults to. That's why. There's not a better reason than that. I'm just trying to make it match. Intraclass correlation, we have an estimated random intercept variance of 1.95, so I can throw that in my ICC formula with 3.29 as my level 1 residual. So this is in logits. But in logits, the amount of variance that is due to school mean differences in the probability of a student getting free lunch is 37%. So you can still talk about the ICC in the same type of way. If I want to convert the predicted intercept back to probability, here's a way to do that in R by accessing the stored coefficients with the fixf function within Glimmer here. I could not get it to do a likelihood ratio test. I think eventually I figured it out, but I left this in here anyway. I did it manually, just by accessing the stored log likelihoods. So if ANOVA or RANOVA or any of those don't work, you can always just do it manually. All right, then we add level 2 fixed effect. So I'm going to add cluster mean math that I have rescaled so that the slope is going to be a change in the logit per 10 points of math. That way the numbers don't get too small. Still in 7 points of integration here. So my coefficients right here are in what scale? Logits. What the model gives you directly is in logits. So minus 1.47 is the estimate for the fixed intercept. How do I talk about that? Minus 1.47. It's in Logits.
Predicted outcome.
It's the
for-
predicted outcome.
For the schools with a cluster mean MAD equals 50.
Yep, for school
and
50.
with random intercept variance equals 0.
Random intercept equals 0, not variance.
Yes.
Yes, yes. The U equals 0. That's the other piece of it that we have to add on here. That's the unit-specific interpretation.
Less free lunch, higher math, or
So this is an intercept. So this is the logit of the probability of getting free lunch for a reference school, because right now there's no person predictors in the model.
yeah.
Yep. Okay. And so to figure out what that would be, we have to take that number and convert it into a probability. So e to the logit over 1 plus e to the logit is how you get the probability, the inverse link. I think I have that. I asked for it somewhere, at least. Yeah, that one. So minus 1.47 in logits corresponds to a probability of 0.187. So not a high probability of getting free lunch if you go to a school whose math is 50 and whose random intercept is 0. How about my slope? Minus 1.44. As school mean math goes up, what happens?
The predicted logit of the conditional mean decreases.
Yes, the predicted logit is lower, or decreases, by 1.44 logits per 10 points of math, because that's what a unit is in this rescaled predictor. So the higher the school math, the lower the probability of getting free lunch. I can turn that into an effect size, which is 0.236 as an odds ratio. The odds for the intercept are 0.230, so that's the probability of a 1 divided by the probability of a 0 for the reference school. So in terms of what I would report out of this, coefficient and logits, standard error and logits, and then probably a column of odds ratios for effect sizes. So I'd put them all together. So you can get those directly out of Stata by adding OR at the end. And I did that in R by just asking for all the fixed effects to be exponentiated. The predictions are close across the packages, but not identical. So there's more differences in these models relative to what you would get from before. And I also computed pseudo R-square for this model. So before the random intercept variance was 1.9, it's down to 0.77, which is a reduction of about 61%. So 61% of all the differences between schools and the probability of a kid getting free or reduced lunch is attributed to school mean math performance.
If you were writing this from paper, would you still calculate R-square to R-square?
I would calculate a pseudo R-square for any level 2 effect, but not level 1. I would not try to do a total R-square that puts everything back together again, because you're still stuck with the 3.29 problem. On your reading list, I think I gave you one of the Hawks book chapters. He has a formula for a total R-square that's based on the variance in the predicted outcomes. So that's one way I've seen it done, but it's squishy, right? Because it's not real. So this I feel okay with, because these are estimated numbers that can come down, so we can think about them the normal way. But 3.29 will never change. Okay, how we doing? Hanging in there? All right. Zoomers, still with me? I haven't forgotten you, I promise. Okay, got a couple thumbs. Yellow thumbs, excellent. So here's my next model, 4. I'm adding in a level 1 predictor that has been cluster mean centered. So which variance component should this new fixed slope of cluster mean centered math predict? Student math, cluster mean centered. Which variant should it account for?
Residual variance.
Yeah, still the same rule, the one in its equation, just there's no E here. Yeah, it should have explained level 1 residual. Is it going to? It's not. So let's look at the R output this time. The code is all pretty much the same. Here are my fixed effects from the prior model. So the slope for math, for instance, was minus 1.44. The slope for school math, it has become more negative. It's now minus 1.52. It should not have changed. But the reason that it changed is because the total variance in the model had to increase in order for there to still be 3.29 left at level 1. So these two models are not on the same scale. So within cluster math, as I'm calling it here, for every 10 points more math I have than the rest of my school's mean, my probability of getting free or reduced lunch goes down, and this is in logits, so I'd have to figure out what the predicted probability is for particular predictor combinations if I wanted to do that. So the logit of the probability goes down by 0.37 per 10 points more math than the rest of your school at level 1. So this coefficient right here for school mean math, CM math for cluster mean in my notation, is this a between effect, a within effect, a contextual effect, or a smushed effect?
Within? No, that's the between effect.
This is between, you're saying.
Yes,
Okay, how do you know?
because we have the within cluster version of level 1.
Yes, because this is cluster mean centered. So this is a between within configuration. Question?
Yes, a quick one. So
Yeah.
at the beginning of this course, we talked that in general terms, that's a variable centering approach.
Mhm.
So here we are using the mean to isolate both effects, level 1 and level 2.
Yes.
Could we use the median in these cases? That would be the same in this context?
You could use the median, but then I don't think you could, it's not going to be the same partitioning. I don't think you can, they won't be orthogonal,
Oh.
I don't think. Not unless it's like the mean and the median are right on the same spot,
Yeah,
and it would depend on the distribution for that.
wow. Okay, yes,
Mhm.
thank you.
What if reviewer 2 comes along and says, I don't think between effects are useful. You should have a contextual effect instead. And also you need to cite me. I mean, this paper.
Yeah, I love when that happens.
You forgot to cite these 5 papers that all have the same person in common. I have no idea who that reviewer could possibly be. Okay, so reviewer 2 wants a contextual effect. What are you going to tell them?
Between minus within?
Yeah. Do you need to re-parameterize your model?
No, if you use linear combinations.
Yep, just ask for it. So in R, I'm using GLHT because it wouldn't let me use contest 1D. This is another way to do it that I use for regression models. We have between minus within, so the between gets the 1, the within gets the minus 1. In the Stata code, I have the same thing written with a lincom, where the within gets the minus 1 and the between gets the 1. And I can exponentiate that too. So whenever you're doing model combinations like this, linear combinations, order of operations, always compute it first, then take the odds ratio. So you get the slope in logits, and then you can back translate that into odds ratios if you want to. If you try to take the difference of the odds ratios, it won't work. It doesn't land in the same spot. So the odds ratio that goes along with it is E to the difference between the slopes and logits. Okay, so putting it all together, I can talk about this contextual effect in 2 different ways, and I have this in the words that go down below. If I want to talk about it as a difference between these two slopes, I can do that, right? If I want to talk about a contextual effect as a difference, given that that's literally how I made it. Yeah, can I? I'm about to,
Okay.
yeah. So we've decided that this is the between effect, right? And it's significantly negative. And what's this person, this guy? This variable? I'm out of words today. Is this between, within, contextual, or smushed?
Within.
This is within. So this one is also significantly negative. Which one is more negative?
Between.
This one.
Yeah.
So that's the other way you can talk about it. The contextual effect says the between effect is significantly more negative than the within effect, because this is their difference. Yep. One way to talk about the contextual effect, it's minus 1.14 and it's significant. The contextual effect is the difference between these slopes. So I can say the contextual effect tells me that the between slope is significantly more negative than the within slope. I can talk about it that way. That might make reviewer 2 happy. But to hedge your bets, there's one more way you can talk about it, which is the usual way we talk about it in terms of controlling for.
Incremental contribution.
Yeah, let's do that one. So my contextual effect of minus 1.14 is an incremental contribution of what?
Of the effect of math
Of school mean math.
with respect to the original values of math at level 1.
After controlling for the original values of math at level 1. So after you control for the math ability of an individual student, what is the extra contribution of school mean math?
Yeah.
That's the contextual effect. That's minus 1.14. So the fact that they're both significant means that school mean math matters regardless of whether you are controlling for student math. The school has an incremental contribution even after you control for it. This is also the idea of if you took your kid with all their characteristics and you move them to a new school. That's the change in their score. I like that one too.
So, on Tuesday, I made a note, for some variable from the fixed effects table, I don't entirely see which one it goes to here, that something changed that should not have.
Something changed that should not have.
It was either, it shouldn't have changed from before.
Oh, I think we were talking about this effect of school mean math versus the one in the model. They should have been the same number because the between variable and the within variable are uncorrelated. So they both stay in their lanes. The reason that it changed is because adding within school math explained level 1 residual, but it still has to stay at 3.29. So the rest of the model is in like the original price, so to speak, from the Coles analogy. The rest of the model is scaled in terms of what the original total variance would have had to have been in order for there to still be 3.29 left over at level 1. So this is just a demonstration of the fact that these models, after you add level 1 predictors, are not comparable in terms of you can't look at these numbers and say, oh, look, it's bigger than it was before. No, of course it is. It has to be. Okay, words, words, words. How about a random slope? Yeah, we can. Did I break any rules by adding my random slope? Or is this okay?
That's okay.
Is it okay?
I think so.
Why do you think so?
Because you have the cluster mean centered version at level 1.
Yep, because this is cluster mean centered. So I don't have to worry about smushing my random slope because I'm using the version of the variable that only has within information. What you have to worry about is when you have a constant centered variable. If you give it a random slope, that random slope is smushed. Because there's no easy way to add a contextual effect as a random slope. It will likely throw up at you. technically possible, but not easy. Now at this point, I realized that I was getting different answers out of R and Stata, and then R wouldn't do stuff, and it got mad. And I figured out that it was because R doesn't do quadrature past 1 point for random slope models. So this is something that in your final homework, which is going to be over these models, I will tell you explicitly what to put here. But it's going to be Laplace estimation because that gives the closest results across packages. So at this point, I had to go, basically there's a difference between what Stata is doing and what R is doing. And SAS and Stata are still connected in terms of what their endpoints are. The other thing that I had to add to the Stata code, as you might remember, is this thing right here, CoVUN. Do you remember what that does? Unstructured is what UN stands for. The word unstructured means let everything be what it wants. Very rarely. If you're doing some kind of non-standard model where your random effects should not be correlated because they're each like doing something else, maybe. Like the cross-classified models, where the way that they're being estimated is by a series of random intercepts that all have the same variance and no covariance, because it's like hacking it. In that case, you would not want the CoVUN, but otherwise you would. So yeah, don't forget that. That's not a default. In my textbook examples, I stick this in every single model regardless, so I don't have to remember about, like, worry about forgetting it. And I've had people be like, well, that's not very efficient. I'm like, what do I care? I just want it to not be wrong. The book's website, by the way, was written by a ginormous SAS program. I wrote a program to write all the code and to execute all the code and to build all the web pages. That's why it's standard that way, because I programmed it in. So, not any more typing, because it was not done manually. That took me about a year, by the way, to do all of that. Anyway, but that's the important part, because if you don't give people a tool to do it, they're not going to ever be able to do it. So this is a little bit weird. So I have both sets of output here so I can continue to contrast how things are displayed. Stata puts the random variances in one thing, and then it added the covariance in a different box. I don't know why. It just did that. But it also puts the slope first and the intercept second. So that always trips me up when I look at this quickly. Do we need to have a random slope? What do I do to decide if, nope, this thing is significant?
Likelihood ratio.
Yeah, likelihood ratio test. So I'm in quadrature, which means I can do that. No, I'm not doing quasi-likelihood. So I did the likelihood ratio test in Stata, told me 38. P is 0 to 4 decimal places, so yep, looks like we need a random slope. In R, I ended up having to re-estimate model 4 so that I would have the same number of quadrature points in both so that they would be on the same scale. I'm not sure if I technically need to do that, but it seemed like a reasonable thing to keep it consistent, so I just did it anyway. So R also came up with a random slope variance of about the same, not too far off. So 0.016 in Stata, 0.0158 in R. So in this case, I also have a point of comparison over here with SAS output, because SAS gives an extra column that I could not find in any other package, which is known as a gradient. In these models in SAS, the gradient is the first derivative with respect to that parameter of the likelihood function. So that means that if your estimate is really at the top of the most likely place, the first derivative, the slope should be 0. So what this is telling me is that, hey, stop that. It came up with the number for the random slope, but it's not really sure what it should be. So on the whole, the model converged with like the overall height, but each individual parameter could converge or not, essentially. So this is useful diagnostically. If things start going haywire, you look for the ones that have the high gradients, and those are the things that are breaking your model. So it's not entirely sure that this should be the number for the slope variance, is what this is telling me.
Is there like a cutoff of like, if they're below this, it's fine?
Not that I know of that would work for every situation. I think of these as just relative values, like the ones that are the biggest problem. But this is not, I could not find this output in any other package, so this is a Glimix thing that it does. It means it's like on the other side. Yeah, it overshot 0 and it's like sitting like this. Yeah, 0 is flat as at the top. Yeah, see now you're realizing the depths of my non-physics capabilities, right? You can't do everything, right? It is, right? Calculus is your friend. See, I took one calculus class in college, and I took the business version because I was going to be a psych major, and psych majors don't need to know math. So I'm just going to get this requirement out of the way, and then I'm going to go be my psych major. Oh, I wish that Lisa could talk to this Lisa. I would have made very different choices about that. But such is life. All right, so R has also decided that it likes this model better. And we can do a couple different things for effect size. So I can make a random effect confidence interval. I did that. So the middle of it is the fixed slope. 1.96 times the square root of the random variance that goes with it. So these numbers I think are from the R output. Gives me this interval in logits. So that means that the change in the logit of the probability of getting free or reduced lunch per 10-point increase is somewhere between these two numbers across 95% of my schools. So the fact that it's negative the whole way indicates that there is an inverse relationship between math and free lunch that's consistent across the schools. Like everybody gets this decrement, so to speak. Note that I don't have probabilities here. I can't. You cannot take a slope and talk about it in terms of probability. And since everybody had such fun with this, I decided to bring random slope reliability back. It's like Throwback Thursday. Throwback all the way to homework 3. That was last week. Can you believe that? It feels like a month ago already. So the formula here, random slope reliability on the numerator divided by that plus residual variance at level 1. So we got to stick 3.29 in for that. Level 1n is the average number of students per school. In this data set, that's 139. And then var here, that is the variance of the predictor the random slope is attached to. You have to have that as part of it because a slope is scaled of units of y per units of x. So you've got to have units of y and units of x. So units of y is the residual, units of x is right here. So this is an index of essentially kind of like an ICC. It's like of the total variance that's related to slopes and residuals, how much of it is related to slopes? It's about 0.63. So that's another thing you can do to try to describe the strength of your effects. Not just that it's significant, but that this is how much it is. Yep. 2.5 is the variance of within cluster math that it's the slope for. So I added that descriptive statistic output to the beginning of this handout to make sure that you could see where that came from. Okay. How about explaining the random slope variance? Could we do that? Why is it that some schools have a bigger effect of math on free lunch than others? Well, I don't have any other information in my data set, but I can throw in school mean math. I have one predictor. That's it. I'm making the most of it though. Look at how much I've done with one predictor. So we're still using 7 points of quadrature. R is using 1. But I added 2 new interaction terms. This one right here, what is that?
Cross-level interaction.
This is a cross-level interaction between a level 1 predictor and a level 2 predictor. So that gamma 1,1 corresponds to this term, school math times within cluster math. So this is asking if the within effect depends on school mean math. I'm also asking if the between effect depends on school mean math, and that's the quadratic term. Do I have to have that in here?
Not necessarily.
Not necessarily, but if I'm asking if the within effect is moderated by something, it seems reasonable to ask if the between effect is too. If I leave it out, I'm assuming it's 0. There's no smushing problem because I'm in cluster mean centering land. Now, which variance components should these two new fixed effects be tackling?
Random and slope variance and random intercept variance respectively.
Yeah, so this one right here that I have highlighted still, what should it explain?
Random intercept variance.
Yeah, the U in its row. So this is a linear effect of school mean math. This is a quadratic effect of school mean math. They both should be explaining random intercept variance. Cross-level interaction is in the equation for the level 1 slope, the within school effect of math. So it should be explaining the random slope in its equation too. And if U1 were not here, then what would it explain?
Nothing. Well, it would try to explain residual variance, but
It would try to
cannot
explain
reduce it.
residual, and it would fail, but the rest of the model has to grow. Yep. Look at what we got, significant cross-level interaction. Okay, what kind is it? Make this as big as possible so we can see the numbers. Okay, so this within school math slope, that is now specific to two things. What are they? I'll give you a hint. One of them's right here. This is the within school math slope, specifically when its moderator is 0. So for a school that has mean math of 50. What else is this conditional on?
random and slope equals 0.
Yeah, the random slope of 0. This is the unit-specific idea. This is a new thing. So it's not just conditional on the interactions with it, it's also conditional on the corresponding random slope being 0. This is a negative number, right? See, it's 140. We're starting with the softballs. This is a negative number, right? Yes, okay. Cross-level interaction, moderating it, also negative. What pattern is this?
More negative.
More negative. Is the effect of within school math getting stronger or weaker as the moderator goes up?
Stronger.
Yeah, more negative.
More negative, so weaker.
Stronger.
We got two different opinions.
I was definitive though, even
You-
if I'm wrong.
That's right. Better to be wrong than vague. It is. Because I can work with wrong, I can't work with vague, right? In terms of like correcting misconceptions or anything like that.
Yep.
So more negative and more positive as a general rule. Those are strongers.
Damn it.
Yeah, but thanks for trying. I appreciate the effort. Less negative and less positive are weakers.
Okay.
I once had a student argue with me about this, that the idea of, like, if I'm on the number line, right, and I have a negative number, and it becomes less negative as I head over and I cross 0, then it becomes more positive. Like if I'm heading in one direction, I'm doing it the right way for you guys, right? No. Okay. If I start, this is positive, and I go less positive, eventually I hit more negative, right? And if I'm going the other way, if I'm going less negative over to positive, do you know why I say it that way, though? Even though technically you're heading in the same way? Because it means something different. So for those of you who are experiencing an Iowa winter for maybe the first time or not that often, when you look at the forecast, it says things like, not as cold. It does not say warmer. If you have a forecast of yesterday was 20 degrees and today is 30 degrees, it says not as cold. That's like less negative. Because people would get angry if it said, oh, it's gonna be hot today. It's 30 instead of 20. That's terrible. Same thing in the summer, not as warm. That's what they say. So that's why I stick with less negative rather than, heading in one direction on the number line. All right. Exactly, like the original slope is negative, so that's your reference point. So what's happening then is that this slope is becoming more negative by this interaction coefficient per 10 points of math, which is a unit of the moderator. So it is, in English, math matters more. Being smarter than the rest of your school in math matters more if your school is smart. Smarter than other schools, that's what I would say. How about this one and that one? Linear and quadratic? They're both negative. More negative, stronger. Yep. That's a negative slope that's speeding up. That's what that would look like. All right, 143. I think that's a good time to ask for questions.
Quick one, because we know that quadratic patterns tend to be like lower than higher,
Yes.
right? So in this case, that would be stronger, but at some point should be weaker,
Yes.
because that would become like a positive effect instead of a negative one.
Yep. So it would be like that. Come on, you can do it. It's like, no, I don't want to draw today. Come on. There. So yes, it's becoming stronger, but if you followed it that way, right, then this is weaker. So it's kind of the same argument as to like which direction you have, because there's really only two U's, right? There's the happy one, and then there's the sad one. So if you start from here, this U, this is a more negative, this is a less positive. You start from here, this is a more positive, and this is a less negative. There. He needs a nose. There. Okay. Any other questions? I'm loopy. All right, 145 then. Thanks for being here. Let me know if you need help with your homework. Looking forward to see what y'all are coming up with. Yeah. All right. See you on the other side. Zoomers, yes, you may ask me a question.